Hello, Djordje Romanic here. Welcome to Fundamentals of Weather and Climate playlist. Behind me is a map that gives us the values of evaporation rate averaged over the climatological period 1991-2020 for the month of July. Please check my video on what is climatological period to properly understand what I mean by this. Units are in millimeters per day, so you might ask, how can evaporation rate be millimeter per day? That's unwritten, so to speak, meteorological convention in the following way. What we mean by millimeter here is that it is a column of water 1 millimeter thick over 1 square meter. 1 millimeter of water spread over 1 square meter is also 1 liter of water. And 1 liter of water is also 1 kilogram of water. So if you want, this would be 1 liter, if it is 1 liter of water per square meter per day. Or 1 kilogram of water per square meter per day. But this per square meter is omitted because of historical reasons, because we indirectly know it is per square meter, so we only write millimeter or liter, depending on literature. So that's the evaporation rate. This is longitude, this is latitude. What do we observe here? We observe that the highest values of evaporation are over warm Pacific oceans, particularly the Indian Ocean, Leuven Current here along the west coast of Australia. And you can overall see that Pacific Ocean is warmer than the Atlantic Ocean for a number of reasons. One of them is Pacific Ocean is much wider in the tropical equatorial region, so much more solar radiation is available to increase temperature of this ocean compared to Atlantic. And also Atlantic is more open to the North Pole, so there is a very large loss of heat through ocean currents from Atlantic towards the North Pole. And here the passage between Pacific and North Pole is very narrow between, as you can see, East Siberia and Alaska, here next to Aleutian Islands. I will talk about ocean currents in future sections of this playlist. Also notice that, of course, evaporation rates over oceans are much higher compared to evaporation rates over land. Evaporation rates over desert regions are very, very low, as you can see. And we can also see that evaporation rates are high over tropical forest regions, such as over the Amazon forest or Congo forest over here and so on. And we have very low evaporation rates over cold waters and continents of high latitudes because temperatures are very low. I would also like to emphasize that these are not measurements. These are the so-called reanalysis data. So that's combination of model and measurements. So these values are uncertain when it comes to these absolute values, but give us good representation of comparing land, ocean, different parts of the ocean and so on. So don't attach yourself to these numbers that much. Attach yourself more to pattern. If we go to the next slide, here is again climatological average in the period 1991-2020 for relative humidity at 1000 millibar, which is typically representative of surface values. 1000 millibar pressure surfaces generally at the Earth's surface. So what do we see here? Well, we see that in high latitudes, we have high values of relative humidity, exceeding 80%. You might ask, how is this possible? In the previous slide, you told us that basically there is no evaporation over here. In this slide, if there is no evaporation over here, how is it that we have high relative humidities? This is where you have to connect knowledge from my previous videos to understand it. The reason is, yes, there is very little to no evaporation in high polar regions, but temperature over there is very low. And at very low temperatures, saturation vapor pressure is very low, so that means relative humidity is very, very high and quite often very close to 100%, as you can see here. Now you might say, okay, I understand that, but still, how did water vapor get here to begin with? If there is no evaporation, how did you get any water vapor here? Answer is, that's a good question. Well, in the atmosphere there are winds. So water vapor evaporates from lower latitudes, and then winds transport that water vapor into the polar regions through various wind systems. Some are local wind systems, some are global wind systems, such as general circulation of the atmosphere. All that will be explained in future videos. But that's to answer your question, how does water vapor get here to begin with? We also see that over desert regions, relative humidities are crazy low, below 20%. That's why deserts are so dry. And you can see that deserts are in these subtropical regions over northern hemisphere, and we will study later why that is the case. That is associated with high pressure systems over there that diminish precipitation, and therefore we have very little precipitation over there and very high relative humidities. We can also see parts of Australia being very dry, but we can also see again that the Amazon forest and the Congo forest are characterized with very high relative humidity that is reaching 100%. And lastly, if we look into specific humidity, that actually amounts for the actual accounts for the actual amount of water vapor in the atmosphere at 2 meters above ground level, then we will see that the pattern of specific humidity more or less closely follows the pattern of evaporation rate that we saw on slide 1. We can see high values of specific humidity in low latitudes and then very low values of specific humidity in the polar regions. The highest values in warm oceans. Indian Ocean has very high, as you can see, values of specific humidity. I also told you in previous videos that specific humidity, which is given in grams per kilogram, as well as mixing ratio, vary between approximately 0 and 18-20 grams per kilogram. You can see that the most extreme values are 22 grams per kilogram, so I was right in previous videos about that. Notice again high values of specific humidity in the Amazon forest, Amazon forest over here, Congo forest. And I don't want to show you more slides because I don't want to overwhelm you with this information. I would like to again emphasize that the values here are uncertain because these are not direct measurements that are obtained using some instruments. This is coming from numerical model. So in terms of absolute values, there is a lot of uncertainty. Different models would give you perhaps different values, but the overall pattern is what matters. And this is the last video in our chapter on water and humidity. And in this last video, you see we combine all these concepts about water, humidity, water vapor pressure, and I show you how these variables are distributed across our beautiful planet Earth. Next chapter is on stability and cloud development. Absolutely beautiful chapter, and I'm looking forward to seeing you there. Until next video, goodbye.